Hi everyone, let's take a look at AP1 graphs today. AP1 graphs. I see that there are 7 questions here to get through. Approximately 15 minutes for each of them is what we would budget. So 7 times 15, that's an hour and 3/4. Let's see how long this takes us. Okay, so problem number 1, part A. We're given a graph of f. F is defined on 0 to 7, closed interval. And then we're told that that g is defined in this most interesting way, from 2 to x of f of t dt. Okay. We're then asked to find g of 3. Well, g of 3 would be the integral from 2 to 3 of f of t dt, which is the area under the f curve from 2 to 3. And so the area under the f curve from 2 to 3 is this area here, which looks like 1, 2, and half of 2 boxes, or 3. G prime of 3, well, if g is f and I take the derivative of both sides, I know that g prime equals f with FTC part 1. So g prime of 3 is f of 3, and according to this picture, f of 3 is equal to 2. And g double prime of 3 is the slope of f at 3. And how can I find the slope of f at 3? Well, this function seems to go down 2 over 1, down 2 over 1. And so I'm going to say the slope is negative 2 at 3 on f. Therefore, g double prime is negative 3. Okay, that's part A. Part B. Part B says find the average rate of change in g on 0 to 3. So average rate of change. This isn't average value. This is average rate of change. And so they want g of 3 minus g of 0 over 3 minus 0. Well, luckily we found g of 3 already. We know that that's 3. G of 0. Well, g of 0 is the integral from 2 to 0 of f dt, and that would be negative the integral from 0 to 2 of f dt. So the integral from 0 to 2 is this triangle whose base is 2 and whose height is 4. So I've got 1/2 2 times 4. Don't forget there's a negative out front. So g of 0 is negative 4. So 3 minus a minus 4 over 3 minus 0, and I get 7/3. 7/3 is the average rate of change on g on 0 to 3. Okay, so if that's my average rate of change, then in part C it says for how many values of c on 0 to 3, so we're not looking at the endpoints, is g prime of c. G prime of c, remember we said g prime of c was this graph of f. When is g prime equal to 7/3? How many times does that happen? Well, 7/3 is 2 1/3, and I see on 0 to 3, that happens once, twice. And explain your reasoning. Well, I would say I would write what I just said, which is that since g prime equals f, g prime equals 7/3 happens is g prime equals f equals 7/3 twice on 0 to 3 according to the graph of f. They're really looking for me to make that connection. If you feel like it, you could certainly say something about, drawing this line, and this line of y equals 7/3 intersects our graph of f in 2 locations. That might be better. That would certainly be bulletproof. I don't know that it's necessary to earn the point in this problem. Okay, and then finally for part D, find the x-coordinate of each point of inflection on G. Okay, so G inflection points means G double prime changes sign. Well, we said G prime equals F, and so G double prime equals F prime. Well, I know that I want a change in sign in the slopes of F prime. Oh no, I want a change in sign in the slopes of F. So the slopes of F are positive, the slopes of F are negative, the slopes of F are positive. So I see the change in sign here at 2 and at 5. But I could also do that with G prime. G prime equals F. And since they gave me a graph of F and not F prime, I kind of want to use this, since they say justify your answer. I'm going to use this relationship and say when G prime equals F goes from increasing to decreasing, that means I have a max on G prime equals F, or decreasing to increasing, that means I have a min on G equals F, then G has an inflection point. And this happens at x equals 2 and x equals 5. We go from increasing to decreasing, and then decreasing to increasing. Okay, so there's AP1. Number 1. Let's take a look at number 2. We've got the graph of the function consists of 3 line segments. G is defined as the integral from -4 to x, f of t dt. Find G of -1, G prime of -1, and G double prime of -1, or state that it does not exist. Okay, so for part A, we want G of -1, which would be the integral from -4 to -1 of f of t dt. And that represents the area under this curve between the curve and the x-axis from -4 to -1. So from -4 to -1, I see a trapezoid. The height of the trapezoid is 3. This base is -2. This base is -3. And so I've got 1/2 a height of 3, base 1 plus base 2. You could, of course, stop here and move along. I'm going to have -5 times 3 is -15 halves. Okay, what about G prime of -1? Well, if I use FTC part 1, I can find out that G prime equals F, because I take the derivative of both sides of this. So G prime of -1 equals F of -1, and F of -1 is the y value at -1 on this graph, therefore -2. G double prime at -1 is the slope at -1. But look, the limit of the slopes isn't the same. I have a corner at that point. And so I have to write here that this does not exist, D and E. Does it ask me to explain? No, it says find the value or state that it does not exist. So the slope cannot be found at -1 because the limit of the slopes are not the same from both sides on this graph. Okay, so there's part A. Part B, we're told for the function g defined in part A, find the x-coordinate of each point of inflection on the graph of G on the open interval from -4 to +3. Well, remember what we said in the last problem, that we'd be looking for G prime equals G double prime equals F prime to change signs, but they didn't give me a graph of F prime, they gave me a graph of F, and so G prime equals F is really what I want to appeal to here to guarantee that I get the justification point for this. So what we're going to say is, when does G prime equal F go from increasing to decreasing or decreasing to increasing? And I see that G prime equals F is increasing, G prime equals F is increasing, G prime equals F is decreasing. So only at x equals 1 is an inflection point on G, because G prime equals F goes from increasing to decreasing. Okay, part C. Let H be defined in this other way. We've got an H function now, and H is defined x to 3 of f of t dt. Find all the values on the closed interval for which h equals 0. Well, if h equals 0, that means that this integral equals 0. So when does this integral equal 0? Well, the most obvious, no, I hate using that word. Many people see that the integral from 3 to 3 would be 0, and so that's one that many students find. But if we come and look at this picture, we're defining this integral from x to 3. So here's 3. And if I go from 1 to 3, this positive area and this negative area would be the same, and they would cancel each other out. Okay, so then I know that x equals 1 is another place where the integral would be 0. If I integrate from 1 to 3, this area would cancel this area. Well, what if I didn't start here, but I started back here? Because look, here's two more of those triangles. One positive, one negative that would cancel out. And so I think also x equals negative 1 would be another one of those. Do they ask me to explain? No, they just asked me to find them. So that's my answer to part C. Part D. For the function h defined in part C, find all the intervals for which h is decreasing. Okay, so if we take the derivative, right, because h decreasing means h prime less than 0. So if I take the derivative of both sides of this equation, I see that h prime equals f, and I want to know when h prime is less than 0, so I want to know when f is less than 0. When is f less than 0? F is less than 0 on, and it does say f is less than 0 on Oh, I was careless. Here, let me erase and show you my careless. Okay, we're talking about h of x, and h of x is defined differently than g of x. We're saying that h of x equals the integral from x to 3 of f of t dt. So my constant and my variables on the bottom, h of x is negative the integral from 3 to x of f of t dt. Therefore, h prime of x is going to be negative f of t. So if I'm looking for when h prime is less than 0, what does that mean for f? Well, it means not that f is less than 0, because we want negative f. Negative f is less than 0, which means positive f is greater than 0. So when is f greater than 0? And that happens on 0 to 2. And they do ask for a justification. This is a nice justification, and I would sum it up by saying h is decreasing when h prime equals negative f is greater than 0. So H is decreasing on 0 to 2. And that should be sufficient for number 2. Okay, that's problem number 2. Let's take a look at problem number 3. Are some of these starting to feel the same even after just 2 of them? Let's see how they feel after 3. Okay, g of x in problem number 3. Ooh, let's switch colors again, just cause. G of x is defined this time as 2x plus the integral from 0 to 2 of f of t dt. And they ask us again to find in part A g of negative 3, which is going to be 2 times negative 3 plus the integral from 0 to negative 3 of f of t dt. So that's going to be negative 6. Well, I don't want to go 0 to negative 3, so I'm going to pull out a negative and go negative 3 to 0. So from negative 3 to 0, I see a quarter of a circle. The circle's radius, negative 6 minus pi divided by 4, and the radius is 3. So I got 9 pi over 4 minus 6. G of negative 3. Yes, I like that. G of negative 3. Negative 6 minus 9 pi over 4. Good. Okay, do we need to do anything else there? Find G of 3, find G prime of x. So G prime of x is the derivative of this. The derivative of 2x would be 2. The derivative of this would be plus f of x. So there's G prime of x, and then they want me to find G prime of negative 3. G prime of negative 3 equals 2 plus f of negative 3. F of negative 3 is, according to the graph, 0. 2 plus 0 equals 2. Okay, so there's part A. There was a bunch of stuff to do there. Part B, determine the x-coordinate for which G has an absolute maximum on the interval. Notice the endpoints, negative 4 and 3, are included, and justify your answer. Okay, well, this is going to be a full candidates test in order to find that absolute maximum. Let's think about what we know. We're looking for G has an absolute max. So I really want to look at a G prime sign chart. G prime, we said, would be 2 plus the integral, 2 plus f of x dx. There's, 2 plus f of x. Thank you. I can do FTC part 1. Okay, so there's our G prime, and we want to know when G prime is equal to 0. So 2 plus f of x, which means I'm wondering when f is equal to negative 2. F seems to be equal to negative 2. Never over here. F is positive, f is negative, but only goes to negative 1. So only over here will f equal negative 2. Somewhere here, but I don't see a labeled point there. I guess I have to write the equation of this line, which I learned how to do in Algebra 1 and reviewed in Algebra 2 and in Pre-Calc and in Calc. And then I have to set that equation of that line, which goes down 6 and over 3, down 6 and over 3, negative 6 over 3, or negative 2 is the slope. The y-intercept is 3, so y equals negative 2x plus 3. I want to set this equation equal to negative 2. I want to know when f is negative 2. And so I get negative 5 equals negative 2x, or x equals 5 halves. So I think x equals 5 halves is my only critical point. 5 halves. That's the only place where f equals negative 2, which is the same as g prime equal to 0. And so don't forget we also need to consider these endpoints, negative 4 and positive 3. What can we say about f? F to the left of 5 halves is always bigger than negative 2, and so this would be positive, and to the left, f would be negative, and so this is our G prime sign chart. Okay, so I know that G is increasing and then decreasing. I see a max here. I see min here because the function is decreasing to that point. And I see a min over here. My function is increasing from that point. You may be able to get away with saying the absolute max occurs at x equals 5 halves, because x equals 5 halves is the only max, and then you defend that max by saying to the left of x equals 5 halves, g prime is greater than 0, and to the right of x equals 5 halves, g equals 2 plus f of x is less than 0. But let's explore the candidates test for the moment and see what we can do with that. You know, with the candidates test, we would want to know g of negative 4, g of 5 halves, and g of 3. So do we know any of these values? Well, yeah, no. No, I don't. I would have to plug these values into the original function, g, and see what I get. So this is 2 times negative 4 plus the integral from 0 to negative 4, which is minus the integral from negative 4 to 0 of f. Okay, so the integral from negative 4 to 0, well, there's a quarter of a circle below the x-axis, 1/4 1 squared pi with a minus in front. And then we already had this quarter circle above with a radius of 3. That's 9 pi over 4. And so we end up with 8 pi over 4, or 2 pi. And so that's negative 8 minus 2 pi. Well, that's going to be a pretty negative number, negative 15 or 16-ish. If we plug in 5 halves, then we have 2 times 5 halves plus the integral from 0 to 5 halves. And the integral from 0 to 5 halves, well, I'm going to have to do some computation there. I see from this picture that the integral from 0 to, well, it's the integral from 0 to 5 halves of this linear equation. So can't I just integrate this linear equation from 0 to 5 halves? Negative 2x plus 3 dx. This would be negative x squared plus 3x from 0 to 5 halves. And that's going to be negative 25 fourths plus 15 halves, or 30 fourths. So we get 5 fourths. Okay, so this was 5 plus 5 fourths, or 20 fourths plus 5 fourths, for 25 fourths. Well, this positive number is definitely bigger than the negative number. And now let's extend this integral to 3 and say negative 9 plus 9 is 0. And so we end up with 2 times 3 plus 0 equals 6. Well, this is 25 and 1/4, which is 6 and 1/4. That is bigger than 6. So here, of these 3 choices, this one is my absolute max. Let's take a look then at part, part C. Part C for problem number 3. Part C says find all the values on the open interval where G has a point of inflection. Okay, so we're looking for G double prime equals 0, or G prime goes from increasing to decreasing, or decreasing to increasing. And we said before that G prime would be 2 plus F. So I want to know when 2 plus F goes from increasing to decreasing, or decreasing to increasing. And that's the same as this function goes from increasing to decreasing, just shifted up 2 places. If I take this point and shift it up 2 places, this function is still decreasing there. Here's the point where this function goes from increasing to decreasing, and so I would say x equals 0 is the only place where this function goes from increasing to decreasing, or decreasing to increasing. I have increasing, I have an undefined slope, I have increasing, and now I have decreasing, decreasing, decreasing. So I suppose I have to justify this. Give a reason for your answer. There is an inflection point on G at x equals 0 because G prime equals 2 plus F goes from increasing to decreasing at x equals 0. And that would be my justification. Okay, let's take a look at part D. Find the average rate of change of f on this closed interval. So average rate of change on f, we'd be looking for f of 3 minus f of negative 4 over 3 minus negative 4. So find the average rate of change of f. There is no point C for which f prime of C is equal to that average rate of change. Explain why this statement does not contradict the mean value theorem. Okay, so let's go about finding f of 3. F of 3 is a point on the graph. That's f of 3 is negative 3. F of negative 4 is negative 1. And I've got 7 on the bottom. So, too many minuses there. F of 3 minus f of negative 4, and I get negative 2/7. Okay, so this is the average rate of change on, good, that's done. Next, there is no point C for which f prime of C equals negative 2/7. And that's true because I see only positive slopes here. I have a negative slope here, but this negative slope we determined a while ago was down 6 and over 3. The slope is negative 2. So f never takes on the slope of negative 2/7. And they say explain why this statement does not contradict the mean value theorem. Well, remember the mean value theorem has as its preconditions if f is continuous on negative 3 to 4, negative 4 to positive 3, and f is differentiable everywhere on the open interval negative 4 to 3, then there must exist. But is our function differentiable at every point on negative 4 to positive 3? Well, no, I have an undefined slope here. And no, the limit of the slopes isn't the same from both sides here. So this function is not differentiable on this open interval, and therefore MVT doesn't guarantee me this. And so I would say, since f is not differentiable on -4 to 3, not everywhere. MVT does not guarantee a place where f prime of c would equal f of 3 minus f of -4 over 3 minus a -4. Okay, so there's question number 3. All right, question number 4. Let's take a look at question number 4. Question number 4 says a certain height of a tree trunk has a circular cross-section. Radius r of the cross-section grows at a rate modeled by this function. Oh, what an interesting differential equation to suddenly run across. Okay, so then we're going to say, write an expression involving an integral for the radius r. Well, we know that dr dt equals 1/16 3 plus sine of t squared. Okay, and write an expression involving an integral for the radius r. So if I do my separation of variables, 1/16 3 plus sine t squared dt, and then I integrate both sides, I get that r of t equals the integral of 1/16 3 plus sine t squared dt. And they want that on 0 to 3. I guess the radius would be at time equal to 0. The radius is, so minus r of 0 equals 0 to t, and these need to be x's now. So integral expression 0 to 3, use your expression to find r of 3. So r of 3 minus r of 0 equals the integral from 0 to 3 of 1/16 3 plus sine x squared dx. So clearly I'm going to use my calculator on that. R of 0, they tell me in the stem of the problem, the radius at time equal to 0 is 6. So I need to add 6 to this integral, and therefore I get r of 3 equals 6.611. This is a calculator active question. I'm not expected to do this by hand. Shame on you if you try and do that by hand. Ew! Just pull out the calculator and evaluate this integral, and then add 6 to it. Okay, so there's r of 3. Part B. Part B says, find the rate at which the cross-sectional area is increasing at time equal to 3. Okay, so what do I know about cross-sectional area? I know that area of this circular cross-section is pi r squared. And I know that dA dt, that's the rate of change in area with respect to time. That's the thing that I'm looking for. The dA dt is going to be 2 pi r times dr dt. Don't forget chain rule. You got to take the derivative of that outside function, but then you have to take the derivative of the inside radius function with respect to time. Okay, so we want to know what dA dt is when t equals 3. So that's going to be 2 pi r of 3 times dr dt evaluated at t equal to 3. So to find dr dt at t equal to 3, I have to plug a 3 in there. Again, I don't know what the sine of 9 is. I'm going to be using my calculator to figure that out. I do know r of 3, because we just found that in the last part of the problem, part A, 6.611 times what I get from this on my calculator, and I ended up with 8.858. Don't forget the units. This is area, centimeters squared per year. They ask for units of measure. So this, I plug a 3 into here to find this number. R of 3 we found in part A, and don't forget the 2 pi. Okay, what's next? Part C. Part C says evaluate 0 to 3 a prime. Okay, well, Delaney tells me if I do 0 to 3 of a prime dt, that's the same as a of 3 minus a of 0. Okay, so what's the cross-sectional area time equal to 0? Wait, using appropriate units, interpret the meaning of this in terms of, oh, it does say evaluate. Good, so I need to evaluate. I need the area at 3. Well, that's pi r of 3 squared minus pi r of 0 squared. So this was 6.611 squared, and this was 6 squared times pi, and I do that on my calculator, and I end up with 24.200 centimeters squared per year. Wait, centimeters squared per year? No. Centimeters squared. It wants me to use appropriate units to interpret the meaning of this cross-sectional area. This is the change in area from time equal to 0 to time equal to 3. The cross-sectional area, increased by 24.200. I kind of want to check that number. 6.611 squared minus 36 times pi, 24.207. 207. Okay. Centimeters squared from time equal to 0 to time equal to 3 years. They might not give you the answer point if you don't have years and centimeters squared. It does say using appropriate units. Make sure you have those. Okay, there's problem number 4. Let's take a look at problem number 5. Problem number 5 says, oh, this one was called Snoopy because it kind of looks like Snoopy lying on top of his doghouse. Okay. We're told that y equals g prime. We're given a graph of g prime, okay. Consists of a semicircle, 3 line segments shown above. Find g of 3. Well, I notice here in the stem of the problem they give me g of 0. So I think that g of 3 minus g of 0 equals the integral from 0 to 3 of g prime dx. So if I'm looking for g of 3, that's going to be g of 0, which is 5, added on to the value of this integral from 0 to 3 of g prime dx. So integrating from 0 to 3 means adding the quarter circle, whose radius is 2, so 1/4 to pi r is 2 squared, plus that triangle, 1/2, base is 1, going from 2 to 3, and the height is 3. So I've got 4 divided by 4, I get 1.5, 6.5, 13 halves, that's 6.5, plus pi. That's g of 3. They also want g of negative 2. Well, g of negative 2 minus g of 0 equals the integral from 0 to negative 2 of g prime of x dx. Again, though, I don't like integrating from 0 to negative 2. I would rather say that g of negative 2 equals g of 0 minus the integral from negative 2 to 0 of g prime of x dx. Okay, so the integral from negative 2 to 0 is that quarter circle again. So I've got 5 minus pi as my answer for g of negative 2. Remember, this is a quarter circle, and I have the work for the quarter circle there. Okay, so that's part A. Part B for number 5. Number 5, part B. Find the x-coordinate of each point of inflection on the graph of g. Okay, so when g prime goes from increasing to decreasing or decreasing to increasing, g has an inflection point. So where do we see that happening? Increasing, increasing, up, decreasing. There's an inflection point at x equals 0. Decreasing, up, increasing. There's an inflection point at 2. And increasing, up, decreasing at x equals 3. So we have g has inflection points at x equals 0, 2, and 3 because g prime goes from increasing to decreasing or decreasing to increasing at those points. This should be sufficient, but if you feel like you have time and you're feeling a little paranoid, you can certainly write the justification for each of these inflection points separately. It will take a little more time, but it would be bulletproof. This should work. It should be sufficient. In the last few years, this has always been accepted, but I do recall a year where some years ago where they really wanted each one explicitly defined. Okay, so there's part B, inflection points. Part C. Part C says H is defined in this interesting way. 5C, H equals G minus 1/2 x squared. Find the x-coordinate of each critical point on H on negative 7 to 5. Notice the endpoints are not included. Okay, that could be useful. And then classify each critical point as the location of either a relative min, a relative max, or neither, and explain your reasoning. So I know in order to find critical points, I need h prime, which means I need to take the derivative of both sides. So that's g prime minus x. G prime minus x. So I want to set h prime equal to 0. So g prime minus x. I still don't know. But if I add x to both sides, then I see this. When does the x value equal the y value on the g prime graph? Here's the g prime graph. When does the x value equal the y value? When does the x value equal the y value? Well, over here, the x value does not equal the y value. And over here, say at negative 4, I'd be greater than negative 1, and that still wouldn't work. Nothing over here will be a case where the x value and y value will be equal. Here, the x values are negative and the y values are positive, so definitely nothing here. But over here, I see x values are positive, I see y values are positive. I wonder if there's a place in here where both the x's and y's have the same value. I kind of want to say pi over 4, but we'll see what happens over there. And then over here, I see the x values are positive, the y values are positive, so maybe again another one or two over here. But now I've got x values that are positive and y values that are negative, so they're not going to be equal to each other. Oh, look at that. The x values and y values are the same. So I know here 3, 3 is going to be a place. That's a critical value. X equals 3 is a critical value. But I also want to find out about this circle. Let's take a look at this circle. Now this circle has a radius of 2 and is centered at the origin. So if I were to write its equation, it would be x squared plus y squared equals 4, or y equals square root of 4 minus x squared. And I'm wondering when this, because this is what y is equal to, I'm wondering when this is equal to x. Okay, so let's square both sides. X squared equals 4 minus x squared. 2x squared equals 4. X squared equals 2. X equals plus and minus root 2. Well, we know minus root 2 doesn't work because at minus root 2, the y value was positive, but the x value was negative. And we need both the x's and y's to be the same. So negative 2 doesn't work, but positive root 2 does work. So x equals positive root 2 is another place where both the x's and y's have the same y value. Okay, so what are we supposed to do now that we've identified these places? We're supposed to identify whether we have a max or a min at each of these places. We've got some places where h prime equals 0, and here's an h prime sign chart with root 2 and with 3. And what can we say about h prime? Well, yeah, so I want to say h prime is g prime minus x. And so over here, this is the y value, this is the x value. The y value is definitely bigger than the x value up to root 2. But between root 2 and root 3, I see on this graph between root 2 here, between root 2 and 3, I see that the y values are going to be, so 2.5 and less than 2.5. I say that the y values are less than, and after 3, the x values are much bigger than the y values, and so I get a plus there. So it is possible for me to do this with a sign chart. I think it's a little challenging to do this with a sign chart. I might find it easier to think about the second derivative test. That might be another way to do this. You know, we know h prime is equal to 0 at these points. What about h double prime at 3? Well, h double prime at 3 would be g prime minus 1. And g prime is the slope here. Well, the slope here, we go down 4 and over 2. Down 4 over 2. So down 4 over 2. And what did I want to do? I wanted to subtract 1 from that. So that's negative 3. I get h double prime of 3 is negative, and because h double prime of 3 is less than 0 and h prime of 3 equals 0, I kind of want to claim a max at that point. But I can't. Why not? G double prime of 3. What was wrong with G double prime? Oh, duh. G double prime of 3. Look, there's a pointy point there. I can't take the derivative at that point. So while G prime of 3 exists, G double prime of 3 does not exist. So I don't know what I was looking at for that. This is G double prime of 3. That does not exist. So I think that h double prime of 3 is undefined because g double prime of 3 is undefined, and so I have neither a min nor a max there. It would seem... Why did I think this? I'll go back and check that in a minute. But if I check h double prime at root 2, that's going to be g double prime at root 2 minus 1. G double prime at root 2 was root 2, right? Because the x and y, oh no, that was g prime. G double prime at root 2. G double prime at root 2. G double prime. Well, G double prime is negative. Because G prime is decreasing. So G double prime is negative, minus 1 is negative, and I would say that this is less than 0, and therefore I have concave down and a 0 slope, which would seem to be a maximum there. And that's what I found on my sign chart. Let's go back here and look to the right of 3 for a second. To the right of 3. So, for example, 5. If I plug in a 5, plugging in a 5h prime means I need g prime of 5. The slope here is negative 2 minus 5. That's still negative. Negative 2 minus 5 is negative 7. So I get a negative here as well. So I don't have a sign change here. Therefore, I have neither a min nor a max. Okay, so you can choose to justify your max at root 2 with h prime, or you can justify your max at root 2 with the second derivative test. You also need to say something about no max nor min at x equals 3 because no sign change on h prime, or you can talk about g double prime of 3 minus 1 being undefined. Okay, so that's 5C. We've only got 2 problems left in this packet. Let's see what the first one is. 6 says, let f be a continuous function consisting of these line segments, a semicircle centered at the origin, and g is given as the integral from 1 to x of f of t dt. Okay, it is known that g equals this integral. Oh, people spray painted on the walls around the community. Find g of 2. 6a, g of 2 will be the integral from 1 to 2 of f of t dt. Okay, the integral from 1 to 2 is, how do I find that y value? Well, I have to write the equation of that little line segment. That line segment has a slope of negative 1 over 2, and x plus b equals y. And I'm going to plug in 0, 1 to help me find b. So b equals 1/2. This is the thing that I'm integrating from 1 to 2. I guess I could just use the area of a triangle from 1 to 2. If I plug a 2 in here, these 2's cancel. I get negative 1 plus 1/2 is negative 1/2. This is 1, this is 2, so that distance is 1. And so the value of this integral then is going to be negative 1/2. Oh, but I had negative 1/4. What did I miss? Oh, I forgot that it was a triangle. 1/2 base times height. There we go, negative 1/4. That's g of 2. Now they want to find g of negative 2. So that's going to be the integral from 1 to negative 2 of f of t dt, which is negative the integral from negative 2 to 1 of f of t dt. So from negative 2 to 1, well, from negative 2 to negative 1, I have this triangle. And from negative 1 to 1, I have this semicircle. So let's think about the areas of these things. So the minus the integral from -2 to -1 dt plus the integral from -1 to 1 f of t dt. Okay, so this integral is 1/2 1 times 3, because I'm just doing the area of the triangle. Now, the integral from -1 to 1 is half of a circle whose radius is 1, so pi r squared, pi 1 squared, would be pi divided by 2, so pi over 2, but because I'm below the x-axis, this is minus pi over 2. And remember, there's that minus out in front. So when I distribute that minus, I get pi over 2 minus 3/2 as my value for g of -2. Okay, there's 6a. What about 6b? 6b. 6b says g prime of -3. G prime of -3. Well, I'm told that g of x equals the integral from 1 to x of f of t dt. And using FTC part 1, I know that g prime equals f of x. So g prime of -3 equals f of -3. F of -3, according to this graph, I don't know. I've got to write the equation of another damn line. Okay, this line passes through -4, +1, and -2, +3. And that means I go 3 minus 1 over -2 minus a -4, which is 2 over 2, or 1. Y equals 1x plus b. 3 equals -2 plus b. B equals 5. Y equals x plus 5. Huh. Okay, now I need to know, I just needed to know the slope. The slope g prime of -3 is f of -3. Oh no, this is the f. And so -3 plus 5 equals 2. That was a lot of work. And then they want me to find g double prime. So g double prime of -3 is going to be f prime of -3, and we found f prime already, and that was equal to 1. Okay, so part C, find the x-coordinate for which the graph of g has a horizontal tangent. Okay, the graph of g has a horizontal tangent. That means g prime equals 0. The graph of g has a horizontal tangent. A horizontal tangent has a slope of 0, so g prime must equal 0. They want to know when g prime equals 0, and we said that g prime, according to FTC1, was f, so we're looking for when f equals 0. Well, f equals 0 at x equals -1 and x equals 1. These are places when f equals 0. For each of these, determine whether you have a max, min, or neither. Okay, well, we've got this nice g prime equals f sign chart here because -1, 1. I see that f prime that g prime equals f is positive over here, is negative in between, and positive over here. And so I'm going to say that I have oh, I wish I would actually read the graph. Look, the graph is below the x-axis, the graph stays below the x-axis. Why am I writing a plus here? This is minus to minus. So I have neither a min nor a max here at 1, but I have a max at -1. Do we have to justify? Yes, justify the answers. There is a max on g at x equals -1 because at x equals -1, g prime equals f. No, because on to the left of x equals -1, because to the left of x equals -1, g prime equals f is greater than 0, and to the right of x equals -1, g prime equals f is greater than 0. Okay, what's next? We need to do the other one. Okay, so there is neither a min nor a max at x equals 1 because there is no sign change in g prime equals f at x equals 1. Great, there's part C. Finally, part D for number 6. Part D says, on the open interval from -4 to 3, see, they don't want us to consider endpoints because you can't have an inflection point at an endpoint. G has a point of inflection. Explain your reasoning. Well, we've said a couple of times in this video that when G prime equals F goes from increasing to decreasing or decreasing to increasing, G has an inflection point. And where does that happen? Well, I see G prime increasing and then G prime decreasing, so at -2. I see G prime equals F decreasing, then G prime equals F increasing, so I have another inflection point on G at 0, and then G prime equals F increases, and then G prime equals F decreases at x equals 1. And so I say at x equals -2, x equals 0, x equals 1, G has inflection points because G prime equals F goes from increasing to decreasing or decreasing to increasing at those points. Again, you could write justifications for each of these inflection points separately, but this should be sufficient to earn you the points. Okay, last question. An oldie but a goodie. Number 7, part A. On what intervals, if any, is f increasing? Now, this is a graph of f prime given, and so when f prime is greater than 0, f is increasing. And I see that that's happening on -3 to 2. And do they ask me to justify? They say, yes, justify your answer. So f is increasing on -3 to 2 because f prime is greater than 0 on -3 to 2. Nice. Easy points for us. Okay, part B. Part B, find the x-coordinate of each point of inflection on f. Okay, so when f prime goes from increasing to decreasing or decreasing to increasing, f has an inflection point. Where does that happen? Well, I see this graph of f decreasing and then increasing, so x equals 0. And then I see this graph increasing and then decreasing, so x equals 2. I see x equals x equals 0 and x equals 2 would be points of inflection for number 7. Yes. Okay. Do I have to justify? Justify your answer. So, therefore, f has an inflection points at there. Good. So f prime goes from increasing to decreasing or decreasing to increasing at these points. Therefore, f has inflection points. Okay, 7c. 7c. Find the equation of the line tangent to the graph of f at 0, 3. Okay, so what do we need in order to write the equation of a tangent line? We need a point and a slope. I need f prime of 0. F prime of 0. Hey, this is a graph of f prime, and the y value on this graph at 0 is negative 2. Therefore, f prime of 0 is negative 2, and that's the slope of my tangent line. So y minus 3 equals negative 2, x minus 0, or if you prefer, y equals negative 2x plus 3. Okay, there was part C, and then finally part D. Part D, find f of negative 3. F of negative 3, here's Delaney's favorite FTC part 2 then coming into action, because they've given me f of 0. So I know f of minus 3, f of minus f of 0 equals the integral from 0 to negative 3 of f prime of x dx. Well, I don't want to integrate from 0 to negative 3, so I'm going to do negative 3 to 0. And what do we know over here? We know f of 0 equals 3. Too many 3's for me. And we're looking for f of negative 3. So f of negative 3 will be 3 minus the integral from negative 3 to 0 of f prime of x dx. So from negative 3 to 0, I see two triangles over there. I see 1/2, a base of 1, a height of 1. And then I see 1/2, 2 is the base, and the height is negative 2. We go down 2 there. So this is going to be negative 2 plus 1/2, which is negative 3/2. And then we have this minus 3 in front. And so we get 4 and 1/2. 4.5 is our value for f of negative 3. We still need to find f of 4, but I'm going to use that same FTC2 approach in 7D. F of 4 minus f of 0 equals the integral from 0 to 4 of f prime of x dx. We know that f of 0 is still 3. So if I add 3 to both sides, 3 plus the integral from 0 to 4 of f prime of x dx. Now, about this integral. Remember, this integral is going to be the area between the curve and the semicircle. I do not encourage you to integrate this curve. I encourage you to find the area of this rectangle and subtract the area of that semicircle. It's going to be much easier. Okay, so that rectangle has a length of 4, and a width of negative 2. And that means negative 8. Now the area of the circle, well, it's only half a circle, but the radius of that circle is 2. So pi over 2 squared. Right, so there's the area of the full circle. We have half of that area. So our area is 2 pi, but we're below the x-axis, so we're subtracting, so minus a minus 2 pi. And so I'm going to end up then with, oh, don't forget this 3 out in front, negative 5 plus 2 pi. Oh my goodness, look at this sine experience. All right, let's think about it. This is the rectangle minus the semicircle. The rectangle minus the semicircle. So the rectangle was negative 8 minus the semicircle, because it was below the axis, was negative 2 pi. Minus a minus is plus. So I've got positive 2 pi minus 8 plus 3, and there's my my f of 4. And that's AP1. Now, what I hope you got out of AP1 was a couple of things, like how do I find g of 3, g prime of 3, g double prime of 3. What can I say about inflection points? Oh my goodness, when f prime goes from increasing to decreasing or decreasing to increasing. This was, I think, a really solid review of increasing, decreasing, inflection points for us, as well as evaluating using FTC 1 and 2. I hope this helped, and don't worry, we've got 15 more of these to go. Have a great day.